All right. I didn't quite get to this yesterday, but it was in your reading. This is an ECG. An ECG is basically taken by little electrodes that you put over your chest that record the electrical activity that's going on in the heart. And what you see is a thing that looks like this. You see the little P wave, what they call the QRS complex, and then the T wave. And the P wave is the activity that's going on in the heart when the atria contract. The atria are the top two chambers of the heart. And when they squeeze, they push blood down, that's the P wave. The QRS complex comes from when the ventricles contract and when they squeeze. And you can see by this chart that the QRS is way bigger than the P. And that's because the ventricles squeeze way harder than the atria. After all, the atria only have to squeeze and push blood down to the ventricles. It's not very far. But the ventricles have to give a big squeeze to push blood all the way to the lungs and all the way around the rest of the body. And so they're a lot stronger and a lot more active. And so the QRS, that's when the ventricles contract. The T wave here is when the ventricles relax. So that's ventricular contraction, and that's ventricular relaxation. And that's the atria contraction. And the relaxing of the atria happens at about the same time as the ventricles contract, so you don't see it on the chart.
What's the difference between an ECG and an EKG?
That's a good question. ECG is electrocardiogram, that's the heart. EKG is electroencephalogram, which is a brain wave reading. They used to be both called ECG, and they got them mixed up, so they changed the brand to EKG. How y'all doing?
Good. Gravy.
You can see that this is kind of messed up. This is what it's supposed to look like here. And that's the normal heart rate. You see this in the hospital. If you go into the right room, you'll see somebody hooked up with this, doing these little waves. And you can see that this guy's got a problem. It doesn't look normal. The QRS is real wide. What problem does he have? You see that in your book? Damage to the AV bundle fibers. See, if you become a heart surgeon, you know, you learn what all the abnormal heart stuff looks like on the chart. And so you hook a guy up to an ECG and you look at the waves and then you tell him, you can figure out what's wrong. How many said they were going to be heart surgeons? Just Al?
Just Al.
Is that the same as a cardiologist, or is that like two different jobs?
Two different jobs, but cardiologist studies hearts, and he might also be a heart surgeon. He might go in there and cut too. Page 352 shows the control of the heartbeat that the brain has. Let me turn the slide up so we can see it a little bit better. You may remember from when we studied the brain that the medulla oblongata helps control heart rate. Y'all remember that?
Yeah.
This is the medulla oblongata. And you can see it has wiring that goes here. Actually, this is wiring that goes to the brain. And this is wiring that comes from the brain. So it has wiring that can go here and affect the SA node, which is the pacemaker. And can affect the AV node, which is the secondary pacemaker that sends the signal to the ventricles. And so, and your spinal cord too can have some effect. Your sympathetic nervous system, if you remember that, that controls your fight or flight responses. some effect. So your brain can control the heart, the speed of the heart to some extent. And that's what all these blue lines show. There is also information coming from the aorta here and from the carotid arteries. Those are the arteries in your neck. That goes to the brain and tells the brain how much blood is going by, how fast the blood is going through. Those signals are picked up right here in these vessels, sent to the brain, and now the brain knows how fast the heart is beating and can make correct adjustments if it wants. So your brain can adjust the speed of your heart. But your heart does have its own pacemaker, so even without any information coming in from the brain, the heart will beat at a steady rate of about 1 beat per second. And you know how many beats you get in a lifetime?
2 billion.
Good guess.
9,000.
About 1 billion. You get about 1 billion beats, and then you're done. That's about as long as the heart can last. It starts to wear out. And it's interesting, that's true of most mammals, and even birds. Like a hummingbird's heart beats 20 times as fast as a person, but it lives 20 times shorter, so it's about the same number of beats. Is that interesting? Yeah.
No, it says
tortoises live longer, and they have slower beats. What were you going to say, McClay?
It says 2.5 billion in the book.
2.5 billion?
Mm-hmm.
Huh.
Say.
Well, that's even more than I thought. Okay, the next thing we want to do is take a look at the blood vessels. And this is what an artery looks like, and this is what a vein looks like. They all have an inner layer of cells we call the endothelium. And then there's some connective tissue kind of holding it in place. And then there's a big layer of muscle. And this muscle layer, that's important, because that muscle layer can contract and squeeze the vessel shut. All of your arteries have a lot of muscle in them, and they can squeeze shut. And your body will squeeze shut arteries that aren't needed at the time.
Is that what it rots?
What's that?
Is that what it rots in the skin?
Some arteries are on the surface, but some are very deep. And so, you are not sending blood to all areas of your body at all times. There are some areas of your body that don't need much blood right now. So the arteries are kind of squeezed up. If you tried to send blood to every part of your body all at the same time, if all the arteries in your body relaxed so that they were wide open, you wouldn't have enough blood to send everywhere. So your body has to constantly be squeezing some of the arteries off, not letting blood go there, so there's enough blood to go everywhere else. Like right now, your feet aren't doing much. Most of your feet are just sitting there, so there's probably not much blood going to your feet. Much of the blood is going to your brain right now because you're paying such good attention. You're using a lot of brain. Isn't that interesting? If you want to get the blood, if you are being very active and you're doing some sport or something where you're running around and you need blood to be going to a lot of different parts at once, the heart really has to pick up its pace and start beating a lot faster, pushing the blood a lot faster to get all this blood everywhere so fast. So your heart rate will pick up. Your heart rate will go from standing heart rate of about 50 or 60 to maybe 4 times that. You can get up to 200 beats per minute when you're going real fast. Let's take our heart rate. Let's check what it is. You know how to find your pulse? Here's a good way to find your pulse. Take 2 fingers. Take these 2 fingers, not your thumb, because your thumb has a pulse of its own. And you know where your thumb comes like this, and there's a bump right there where your wrist is? If you touch that bump and then go a little bit down, you should be able to find a pulse right there. For some people, it's harder than others. Kind of go a little bit down from the bump on your wrist. Can you find it? Max found it. Kate, you got it? Each pulse is a ventricular contraction. And we have a name for a ventricular contraction. It's called a systole. Systole is the contraction, the squeezing of the ventricles. Do you know what it's called when the ventricles relax?
Dystole?
Good guess. Diastole. Systole is when the muscle contracts, and diastole is when it relaxes. So every time the ventricles of your heart contract, specifically your left ventricle, every time it contracts, blood is pushed through your veins, and it makes a little pulse that you can feel. And so to take your pulse, you simply look at this clock, and you start counting the number of beats when it reaches, let's start when it reaches 9 there. Ready, go. I missed it, Okay, stop. How many did you count? Somebody yell out a number.
13.
13, and you multiply it by 4 because we only did 15 seconds. And so 13 times 4, state championship math team? 52. Very good. See why y'all aren't on the team. Anyway, so 52 beats per minute for somebody. Anyone have different than that?
Nope, that's it.
You had 10? 40 beats per minute? That's pretty low.
18.
18? Okay. Generally, the slower your heart rate is, the larger your heart muscle is. And so, with each stroke, it's pushing. If you have a low pulse rate, with each stroke, your heart is pushing a lot of blood. Usually, a bigger person will have a higher stroke volume. And often, athletes, if you do, especially if you do sports that require lots of oxygen, like running or swimming or something like that, long distance running. If you're into that, your heart muscle will get bigger and stronger, and you'll push more with each stroke, so you don't need as many strokes per minute. They said Lance Armstrong had the lowest ever recorded standing heart rate. It was a biker. It was like 29 beats per minute.
What?
Pretty amazing, huh? So,
maybe it was the drugs that was doing that.
The drugs? Yeah, it could have been.
Or the rugs.
If you look at veins don't have the muscles in their outer walls that the arteries do. Veins don't really squeeze off. Because the body's worried about sending blood to a place, not recovering it as much. So there's not much muscle in the walls of the veins. There's a little bit, and it could squeeze a little bit, but there's not much. The veins also all have valves, one-way valves to keep the blood moving. You see, the veins are very far from the heart's pump. In other words, the heart pushes blood through arteries, and then through smaller vessels called arterioles, and then through capillaries where the oxygen is delivered, and then venules, and then finally veins. And as the blood finally gets back to a vein, it doesn't have much pressure. So the veins are very low in pressure. And to keep the blood moving, you have to have these one-way valves so the blood can't go backwards. And it especially helps the veins move if you move your body a lot. If you stomp your feet or shake your arms, it squeezes these veins a little bit, and the veins and the blood gets pushed forward because the blood can't go backwards because of the valve, so it can only go in one direction forward. So if you really want to get the blood moving, as they say, stomp your feet a little bit, move around, and it helps the blood get back to the heart, to those veins. That's the inside of a blood vessel under a microscope. That's the inside of a blood vessel with a bunch of fat deposited. This is called a plaque. And this person has had a lifetime of junk foods and such, and they are full of cholesterol and fat right here in the vessel. When you eat too much and you don't use all the food you eat, it's stored. A lot of it's stored under your skin as fat. Some of it's stored in your blood vessels as fat. And you can see blood won't flow very well through that, not nearly as well as it would flow through that. So this person right here is going to have what's called high blood pressure. And that can be a danger. And if it gets completely stopped up, then the blood will be cut off from going to where it's needed. And that can cause things like heart attacks and strokes and that sort of thing. The doctors can give a drug that will help bust up clots and stuff that block the area. But to get rid of all this fat, really the best way is exercise and diet. They can actually go in with a little instrument, a little balloon connected to a line, and move it back and forth inside the vessel and kind of rub away and open up this area some. But most likely, when you get older, this is what your blood vessels are going to look like. Because all of us have extra weight. Almost all of us have some extra weight when we get older because we're not as active. So if you want to have clean arteries, eat well, don't eat too much fat, and make sure you exercise a lot. There's another look at a blocked vessel, a clogged vessel. And here's another look at a clogged vessel. That's the fat that's built up. And see, the cells will grow right over that fat. And so your vessel just gets smaller. We already saw, that was about the heart attack we already saw in the video. Here it shows your smaller arteries called arterioles. The arteries leave the heart and then they branch off and get smaller and smaller. And eventually they get so small they're called arterioles. And they have these pink things are muscle that surrounds the arteriole and can squeeze it off. And the smallest vessel of all is called a capillary. The arterioles will branch down to capillaries. The capillaries don't have any muscles surrounding them. The capillaries are just made of thin cells, and all the nutrients from the blood can squeeze out through these little cracks and go to the cells. Like sugars and oxygen can come out of the blood and go to the cells. So it's at the capillaries where the cells get fed. All your organs, your muscles, your bone cells, your nerve cells every one of them is next to a capillary. So capillaries are everywhere in your body delivering the nutrients to the cells. The cells will give waste into the blood. The cells will squirt waste into the capillaries, and the capillaries will take the wastes away. And then the waste will be filtered out in the kidneys, so you pee out some of the waste. And the lungs will take the carbon dioxide, and you breathe that waste out. You're getting rid of waste right now. I just breathed waste at you. That was some of the food that I ate earlier. Isn't that wild? Here, it shows how it leaks out between the cracks. Water leaks out. Oxygen. And stuff can leak in, too. Waste can leak in. Here's kind of a diagram that shows the arterioles and the capillaries. Capillaries are so small that blood cells have to be single file as they go through a capillary. Thought I had a little video. Hold on, let me see if I missed the video. This might be it. Yeah, this is it. Little video showing you some of this stuff.
The body's source of pressure is the heart, at the center of our fluid delivery system, the blood circulation. Under pressure from the heart, the blood flows outwards in the arteries, the red tubes here, and back along the veins, the blue ones, after it's delivered its supplies to the cells.
That's an artery.
The widest artery is the aorta, with a fibrous muscular wall which receives the full force of the blood as it first leaves the heart. Then, as the blood travels through the body, the arteries get narrower and divide up into smaller and smaller tubes, carrying off the blood supply to different organs. Up to now, the tubes are still just a transport system. But as the blood reaches its destination, the blood vessels become leaky, so that the food, oxygen, and other components can get through to the tissues. These are the capillaries, and they're so small that more than 1 million of them would fit into the diameter of the aorta. Now that the blood has delivered its supplies, it travels back in the veins towards the heart. The blood is no longer under much pressure, and the veins have thinner walls without much muscle. They also have valves in them to help the blood on its sluggish way back to the heart. The important thing about blood in the body is that it's a closed system. The blood gets used over and over again.
I wanted to see the microscopic blood cells. Hold on just a second. Microscopic blood flow.
In the leg, the blood vessels start to get narrower. We are following blood on its way to the foot, where the skin and muscles will need oxygen and fuel. As the blood vessels get nearer to the tissues they have to supply, the muscles in their walls play a crucial role in controlling the blood flow to different areas. The tubes can dilate or constrict to let more blood through or restrict the flow. This blood vessel is cutting down its own blood flow. When this happens, it helps to divert blood to other areas. There are often small rings of muscle where one blood vessel meets another, which open or close like taps. There's one about to open at the top of the screen now. These vessels are opened and closed by hormones in the blood, the chemical messengers that can cause a general alert to cut down the blood flow to the whole area. The muscles in the blood vessel walls are so sensitive that it takes only 1,000 millionth of a gram of hormone in the blood to open or close the taps at each of the junction points. The blood system alters its flow in the same way that this miller controls the water flow through his mill. He has 3 millstones for grinding different types of grain. He can open or close gates like valves to make the water flow through the channel that will turn the millstone he needs. At the top of the screen, another tap closes down and cuts off supplies to an area which doesn't need blood for the moment. From moment to moment, the needs of every part of the body for blood are dealt with by changes like these. It's even possible for temporary bypasses like this to open up, to help shunt blood away from certain areas.
Huh. That was good. Kind of shows you what's going on in there. Most people don't know that blood can shut off. If an area is real low in oxygen, it'll send out a chemical message that'll cause those little muscles to relax and open up, so it can get enough oxygen. So it's not having to do any thinking. It's an automatic process. Isn't this great, y'all? You guys just love anatomy. How many love anatomy? Raise your hand. Okay, everyone with their hand gets an F. Leah.